Well, hello there, and welcome back to The Explainer. I am absolutely thrilled you're joining us today. Now, this explainer is brought to you by the team over at Forge College. And wow, do we have a fantastic topic lined up for you. In our last lesson, we took a really fun little detour into customizing Claude code for Solana workflows, which was a blast, right? But today, we're pivoting right back into our Ethereum fundamentals track. We're getting back into the engine room, so to speak, to tackle a question that literally stumps so many developers when they first dive into smart contracts. We're talking about handling dynamic data structures. Okay, let's dive right into this. Here's our blueprint for today. We're going to look at welcome to dynamic data, memory versus persistent storage, computing the storage slots, building the Python simulation, validating your data traces, and finally, takeaways and next steps. This whole module fits directly into our EVM deep dive on execution and environment. And honestly, trust me on this, by the time we wrap up, the low-level magic of the Ethereum virtual machine is going to make a whole lot more sense.
All right, Section 1. Welcome to Dynamic Data, Packing the Unpackable. So think of managing EVM storage kind of like moving day. Packing fixed-size items, like a toaster or a perfectly square box of books, into nicely numbered boxes, super easy. But how in the world do we manage dynamic data when we don't have contiguous slots? It's like, how do you pack a magical, infinitely growing sofa without completely busting the moving boxes? The EVM, if we're being totally honest, is a bit of a chaotic monster when it comes to memory management. It absolutely does not just hand you an endless row of empty buckets for your growing arrays. So before we even look at the low-level opcode instructions, we really have to master how data dances from temporary ephemeral memory over into permanent persistent storage.
Moving on to Section 2, memory versus persistent storage, the staging ground versus the vault. Okay, because dynamic structures completely break that simple one variable, one slot model, we actually have to rely on an entirely new pattern of indirection. Take a look at the chaotic staging ground of ephemeral memory on the left. It's basically filled with virtual packing peanuts and half-open boxes. It's this volatile buffer where temporary data gets mutated and arrays are built. Now contrast that with persistent storage on the right, which is the canonical permanent EVM state layout. That is a rigidly structured, heavy-duty vault. You don't build things in the vault, no way. You build them out in the staging ground, and then carefully, deliberately move them over. So let's formalize that idea for a second. A memory buffer is an ephemeral staging ground where variable length content is constructed or mutated before committing. And the absolutely crucial word there is committing. There's a very, very precise choreography required here to safely and efficiently commit this volatile data into those persistent storage slots, and you've got to do it without wasting a ton of gas or, worse, corrupting your state. Which brings us to Section 3, computing the storage slots, deterministic addressing. Now, you might be wondering, since we don't have those contiguous named slots for our dynamic data, what do? Well, we use hash-derived addressing, and central to this whole concept is the slot hashing function. I want you to imagine a highly organized, but frankly totally eccentric librarian. Instead of using the normal Dewey Decimal System, this librarian uses intense cryptographic hash functions to decide exactly which shelf and which book spine your specific data belongs to. I know it sounds a little crazy, but it's brilliant, because it guarantees that data never accidentally overlaps. Let's break down the math for dynamic arrays first. As you'll see, the base slot is simply the hash of the 32-byte representation of the variable slot. Let's put that into perspective with a concrete example. Say your array is assigned to variable slot number 5. We take that number 5, pad it all the way out to 32 bytes, and then we hash it. That massive, crazy number we get back, that is our base address. Now, to find where the actual elements go, we literally just numerically add the index. So element 0 is at the base slot plus 0. Element 1 is base slot plus 1, and so on. It's actually beautifully simple once you have that base figured out. But mappings? Mappings are a bit of a different beast. Contrast that array math with this mapping formula. For a mapping, the entry slot relies on concatenating the specific key bytes with that 32-byte big endian base slot, and we do this before we hash it all together. Why? Because a mapping doesn't have a contiguous length, right? It's really just a bunch of disjointed key value pairs floating around. So every single entry absolutely requires its own unique hash calculation. All right, Section 4, building the Python simulation, drafting the blueprint. Now, theory is great and all, but to really, truly grasp this, we're going to build a reproducible simulation script using Python 3. Here's our 3-step construction manual. Phase 1 is going to set up our memory primitives. Phase 2 will be our slot computation helpers. The math we literally just talked about. And Phase 3?
That'll be our commit routines. This engineering blueprint is going to give us a perfect working model of the EVM's memory to storage pipeline. Quickly looking at phase 1, our core memory functions are incredibly straightforward. We just need to allocate memory, write to memory, and read from memory. These primitives simply simulate reserving that contiguous space in our ephemeral staging ground and then writing 32-byte hex strings right to a dictionary. Think of it as our virtual workbench. Next up, phase 2, our math helpers. We implement the array base slot, the array element slot, and the mapping slot computations. Now listen, the absolute most crucial step here, and I mean this is where so many developers completely trip up, is making sure we serialize the base slot as a 32-byte big endian value before we throw it into our deterministic hash function. If your endianness is backwards, your data is going to end up in a completely different galaxy inside that storage vault. And finally, phase 3. This is where the magic happens, guys. Our commit routines will sequentially read from our memory buffer dictionary, compute the exact element or mapping slots using those math helpers we just made, and then write those values directly into our storage dictionary. Oh, and as it does all this, it's going to log a trace of every single action so we can see the exact step-by-step lifecycle of our data. Moving to section 5, validating your data traces, checking the build. Now, what's really interesting about this slide is that building the simulation is really only half the battle, right? Inspecting the output is where the actual learning clicks into place. Let's walk through this expected trace table together. If our script is correct, our trace is going to show that array index 0 maps to a specific hex space slot. It reads from memory address 100, and then it stores a specific hex value. Array index 1 maps to that exact same base slot, +1, reads from memory 101, and so on. A beautifully organized trace table like this physically proves that our ephemeral memory reads perfectly match our persistent storage writes. It is also absolutely vital to look at the sequencing of these events. For a successful commit, the trace ordering has to be perfectly exact. We must first see a memory write, actually putting the data into the staging ground. Then, during the commit phase, we must see a memory read, followed immediately by the store event that places it securely in the vault. If this sequence gets broken, well, the whole operation is compromised. So what happens if your trace doesn't look right? Hey, don't panic. Here's a quick troubleshooting checklist for you. Usually, if a trace fails, it's because of a bad 32-byte big endian serialization. Some other usual suspects include off-by-1 errors when adding up your array indices, maybe reversed mapping entry concatenations, or, and I've done this, somehow missing a memory read event entirely. Just go through this list, check it twice, and I promise you'll find the bug. And that brings us to section 6, takeaways and next steps, wrapping up the blueprint. So the crucial point is really understanding the overarching workflow of how the EVM handles all this complexity. Let's wrap up our 3 main operational principles. Just to reiterate our core concepts here. Number 1, dynamic structures do not get contiguous slots. They use deterministic hash bases. Number 2, memory acts as our chaotic, temporary staging ground. And number 3, step-by-step trace validation is basically our ultimate debugging tool to ensure that our data identity actually matches our expectations. And hey, whatever you do, keep your Python script because in our next lesson, which is memory and storage trade-offs, patterns, and synthesis, we are going to use this exact simulation trace to analyze actual Ethereum gas costs, look at instruction-level trade-offs, and really figure out the efficiencies of in-place updates versus full memory commits. It is going to be absolutely fascinating. I want to leave you all with this powerful thought. The mental model of a buffer traversed and written into computed slots is the bridge between high-level solidity semantics and low-level EVM execution. Once you truly visualize that bridge in your head, writing hyper-efficient smart contracts really does become second nature. But this begs a pretty fascinating question. If writing from memory to storage is so incredibly complex and expensive, what kind of bleeding-edge patterns are developers out there creating to bypass persistent storage entirely? Ponder that one until next time. Now, this explainer was proudly made by the team at Forge College. For more deep dives into this subject, and honestly a wealth of other awesome Web3 topics, be sure to visit our website at forge.college. Keep exploring, keep building, and I will see you in the next one.